right, let's talk about polar equations. Now, the cool thing about polar equations is they can describe things that would be really hard to describe in the Cartesian system. So let's start with something that just looks like r equals to theta. How are we going to graph this? Well, we don't know a thing about graphing in polar coordinates yet. That's what we're trying to figure out. So we're just going to make a table. And our table is going to be a theta and an r. Okay. And I don't have any labels on my spokes here, but let's see. Pi over 3. This is pi over 4. That's fine. Let's just do this. So let's say theta is pi over 4. R is 2 times that, which is pi over 2. If theta is pi over 2, my r is pi. If theta is 3 pi over 4, my radius is 3 pi over 2. If theta is pi, my radius is 2 pi. You get the idea, yeah? Okay, so I'm just going to take the easy way. And this is pi over 2. This spoke is pi over 4. This spoke is 3 pi over 4. This spoke is, of course, pi. 5 pi over 4. 3 pi over 2. 7 pi over 4. And 0 or 2 pi. Okay. So when theta is 0, r is 0, I didn't put that one on, but that's okay. All right, and I'm going to make my life simple again. And this guy's going to be pi. Yeah, let's go a little bit further. Let's make that be pi over 2. Pi to be pi over 2. 2 pi. Okay, so when theta is pi over 4, radius is pi over 2. When theta is pi over 2, radius is pi. When theta is 3 pi over 4, my radius is 3 pi over 2. 3 pi over 2 is this one. There we go. When my radius is pi, or sorry, when theta is pi, my radius is 2 pi. When my radius is 5 pi over 4, when theta is 5 pi over 4, my radius is going to be 5 pi over 2, which would be that one. Right, and we could keep going. And what we're going to see that we get is this ever-increasing spiral. The Desmos actually does a much nicer job of graphing, because I forgot to get that point right there. So although Desmos cannot graph polar points, Desmos does just fine with polar equations. Okay? So that is really the skinny on graphing polar equations. You're going to make a table of values and then connect the dots. Now I want to give you some basic shapes. So if we have r equals any number, we get a circle centered at the origin. Okay, so if r equals any number, we get a center circled at the origin. What if you don't want a circle centered at the origin? Well, you can do that by multiplying. If you want a horizontal shift, you multiply by cosine theta. So r equals cosine theta gives you an offset circle. Now, how offset is it? Well, let me turn on some numbers for you. And what you can see is that my radius is not 5. My radius is 5/2, right? So that 5 gives you the diameter of the circle. If you want a circle of radius 5, offset, and in my notice it still touches the origin. Think about why. What if you want a circle that is offset in the vertical direction? Well, you can do that with a number multiplied by a sine function. Oops, it helps if I do that correctly. So r equals, we'll just say 5 sine theta. And remember that the equation r equals 5 just gives you a circle of radius 5. Okay, now you may be wondering, what if I make that -5? Well, if you make it -5, it offsets the opposite direction. Okay, so that's a couple of examples. You can also do we saw a minute ago, you can make the spirals that we talked about. So let me just put a slider on here. And let's turn these guys off. And look at, remember how we did that? We did with that with r equals theta, right? But I want to make it r equals a theta. And I want you to notice what happens if I make theta smaller. My spiral gets tighter, right? What happens if I make theta negative? Well, it spirals the other direction. If I make spiral bigger, my spiral, or if I think theta big, or a bigger, I'm adjusting a. If I make a bigger, my spiral gets looser. Make a smaller, my spiral gets tighter. If I make a negative, my spiral goes the other direction. Okay. There are also things we can do that are called Lima Cons. And I'm going to show you what a Lima Con looks like. So, well, here. Let's say I take my r equals 5 sine theta. But now I want to just add something to it. So let's add a. We've got a slider here. We might as well use it. I get this kind of looped in on itself circle. Now, what happens if I make a bigger? If I make a bigger, my internal loop gets smaller. If I make a smaller, my internal loop gets bigger. What happens if I make a negative? Well, there's no real discernible. What happens is it changes which way you go. So if you make a table of values, you can see whether you start on the inside loop or the outside loop. Okay, this is called a Lima Con. You can make a rose. So how do you make a rose? Well, you make a rose by putting your multiplier inside your parentheses. And that's quite the rose there. Let's make that a 3. There we go. And you can see that the 5 once again gives me my radius. So you notice that you can get all sorts of roses, right? And really the only way to know what size you're going to get, what type you're going to get, is to make a table of values or play with Desmos. So Desmos does some really cool work for us. All right. So Lima Cons, roses. why are some nice and pretty like a 3-leaf rose and some aren't? Well, there's a lot of number theory around that, but it's got to do with whether or not you land on that special known unit circle value on a radius of 5. So anyway, we aren't going to worry about that in this class. Just know that you can use polar graphing to make some pretty nifty things. And if you've ever had a spirograph, you might recognize some of these shapes and think about how spirographs are made, and that will make sense. Okay. In the next video, which will be the last video for this section, we're going to talk about converting between polar and Cartesian coordinate, converting equations from polar to Cartesian and vice versa.